Let's take a look here at a example of resonance in a pipe. In this example problem, simply reads, a pipe that is open at both ends has a fundamental frequency of 300 hertz and the speed of sound in air is 331 meters per second. And then we want to find the length of this pipe, the next two harmonics, and then the fundamental frequency if the speed of sound in the air increases to 300 meters per second due to the rise in temperature of the air. So let's try to picture what's going on here. So the first thing to think about is to realize that in real life, if you want to build an instrument like an organ, you really need to know how to calculate this, because you can't just cut pipes randomly and hope you have this multi-million-dollar organ in a cathedral be in tune. Okay, can't just guess. You're not going to get lucky there. Okay, and in real life, saxophones, clarinets, flutes, you name it, it's all about figuring out how do you get this thing to resonate at exactly the right frequency there. Okay, and what's interesting is sometimes the end of the pipe is closed, so that'll force a node, and then the other end is open. And sometimes, we set up more harmonics. We have pipes where they're open-ended here. Okay, and that actually affects then how it sounds if you cap it versus not cap it. And that's why a lot of times when you play a piped instrument, you push different buttons to close and open up valves and change their lengths and change how it resonates in a nutshell there. So let's break it down. Step one, we draw a picture of a pipe that is open at both ends. So I'm not going to try to draw a saxophone or tuba or flute or whatever. I'm going to draw a pipe, a side view showing that the ends are open. So I guess we can try to sketch that in 3D there. But the important thing is the waveform inside. Okay? If you think about it, if the air can shake a lot at the ends, let's call that antinodes. If there's two antinodes on the end, that means there's this point in the middle where the sound won't shake a lot. And hopefully you remember, or you'll get to this point in our digital audio lab. We're going to do a cool thing where we actually squeeze the middle of a steel pipe, whack it on the ground, and if you get exactly the middle, you actually get it to resonate at its first harmonic, and it makes that cool kung fu ringing sound there. But this picture is super important. Next, let's kind of break down the information in terms of what's going on here. We're given that it has a fundamental frequency of 300 hertz. Fundamental just means that it's at the first harmonic. So let's call that F1 is equal to 300 hertz. We're also given that the speed of sound in air is 331 meters per second. That's its velocity. And normally we can use the speed of sound in air equation if we needed to. When it warms up, it's 331.5 meters per second plus 0.6 times T, which is the temperature in degrees Celsius. But I think in this case, we don't actually have to calculate that in terms of how fast the air speeds up there. Okay? And then we want to find the length of the pipe is the first question. Okay? And let's just do one part at a time there. Okay? We'll call that, actually the length of the pipe doesn't change. So the important thing to realize, though, off the picture here, is there's only one equation that relates velocity and frequency. That's our wave speed equation, which is just simply v, velocity is equal to wavelength times frequency. V equals lambda f. Okay? So the big thing is we need to find the wavelength, lambda 1 of the first harmonic. So it's all in our picture. So notice if we have an antinode, node, antinode, the length of this pipe is equal to half a wavelength. Bingo. So once we find the wavelength, we can get the actual length of the pipe. Okay? So now we're ready to substitute in our information into our wave speed equation. In step 4 here, velocity was given as 331 meters per second. Wavelength we can solve for, is our unknown in meters, so then we can get the length of the pipe. And frequency was given as 300 hertz. Therefore, lambda is just simply equal to 331 over 300. So we'll just get out our calculators and plug that in really quick. And I got 331 over 300. And I'm getting a wavelength, lambda 1 of 1.103. Good enough. Okay, 1.103 meters. Therefore, the length of that pipe is going to be half a wavelength there. So I'll just get out my calculator and just divide the wavelength by 2, and I'm getting 0.552. We'll just round that off, meters there. Okay. And let me just go ahead and substitute in what we just solved for there, 1.103 meters. Next, we need to find the next two harmonics, and then there's a fundamental frequency when the temperature increases. So let's find the next two harmonics. So if we know F1, then we just need to find, in this case, F2 and F3. Okay? So F2 would be the second easiest way we can shake this pipe here. And if you want to picture that, let me kind of sketch this out here. Instead of just one node, we're going to have two nodes in here actually. Okay? That's important to picture. So antinode, node, and we actually have to have another antinode there. Okay? So the important thing is to actually know how to visualize this here. There we go. And I think I whiffed on how I drew the node there. Let me fix that. Okay, so instead of one node, we're going to have two nodes there. There we go. And then get the antinode there. There we go. Bam, and then bam. Okay, so the important thing to realize, it's actually pretty easy once you see it, is here we have an antinode, node, antinode. Here we have, so that was half a wavelength. This is a quarter of a wavelength, another quarter. Here we have a quarter, a half, 3/4, a whole. So in other words, the second harmonic is an entire wavelength. So if we basically we have to shake the air faster, it's going to be a multiple of the first harmonic. So in other words, like before, if you shake it twice as fast, you're going to get twice as many waves in there. Okay, is a way to look at it there. So in other words, instead of doing this mathematically, we could to solve, because we have a new wavelength there. It's just going to be multiples. It's going to be 600 hertz there, because we're shaking it twice as fast. And then the third harmonic will be 3 times as much, would be the way to picture it here. And that's because we have a symmetrical system here. Okay, so this would be 3 times 3 would be 900 hertz. So in other words, to look at it mathematically, if we look at our wave speed equation, frequency would be velocity over wavelength. The velocity didn't change, it's the same pipe, but the wavelength changed. We shoved in twice as many waves, therefore we have to shake it twice as fast, is a way to think of it. Okay, and then if we shove in 3 times as many waves, it's 3 times the number of the frequency there. Finally, last part of the problem. What is the fundamental frequency of the pipe when the speed of sound is increased to 380 meters per second? As you warm up a pipe, the speed goes up because the air molecules are moving faster. So why don't I call this V2? And it's sped up to 380 meters per second. And all we want to do is find the new frequency. Okay, our new fundamental frequency. Well, pretty easy. We can find frequency if we know velocity, and then we just have to divide it by the wavelength. And the wavelength of the fundamental we solve for is 1.103 meters there. So all we got to do is just take 380 and divide it by 1.103. When we do that, we get 344.5 hertz. And if you look at this, this actually makes sense, because as you warm up an instrument, if the air can travel faster, then the molecules can propagate the disturbance faster, then it's going to shake faster. It's a way to picture it. We change the medium there, so the wave velocity increases, so the pitch goes up. So what's interesting in real life is as you warm up a piped instrument, usually musicians have to adjust because the pitch goes up. And so they just kind of learn how to warm up so that when they have to perform, everything's in tune. Whereas a stringed instrument, I think what's a little bit different is as it warms up, the string actually loosens up. So the pitch tends to drop. So usually once a band warms up, they kind of have to retune up their instruments. But anyway, in a nutshell, this is a cool example of applying resonance to a symmetrical open-ended system.